Welcome to the Things of the Stars, Sleeping with Science series. These journeys invite you to slow down, quiet your thoughts, and drift into rest while exploring the wonders of the universe. If you enjoy these moments of calm discovery, support us by subscribing to this channel and visiting thingsofthestars.com. Take a slow, deep breath and imagine yourself drifting down to a realm smaller than any you've ever known. Beneath the everyday surface of things, down past the cells in your body and the atoms that make up the world, lies the quantum realm. It's a place so mysterious that even the greatest scientists approached it with wonder and puzzlement. In this tiny domain, the rules of common sense seem to fall away. Particles can be waves, causes can happen without obvious effects, and things can exist as mere possibilities until we observe them. As Niels Bohr once remarked, anyone not shocked by quantum mechanics has not yet understood it. Don't worry though. Tonight, we will explore these quantum secrets gently and clearly, like a bedtime story of science and awe. Let's float inward together into the heart of the atom. Envision yourself surrounded by a soft glow of starlight-like particles. The world becomes quiet and strange. Here, in the quantum realm, light and matter play a delicate game of hide and seek with reality. We'll encounter wave-particle duality, where things are both particles and waves. We'll touch the idea of superposition, where something can exist in two states at once. We'll meet the ghostly connection of entanglement, which Einstein poetically called spooky action. And we'll see how the mere act of observation can change this tiny world's behavior. A reminder that the observer and the observed are strangely intertwined. Through it all, we'll weave in the stories of pioneers like Albert Einstein and Niels Bohr debating reality, Erwin Schrödinger dreaming up a cat paradox, and John Bell confirming quantum truths in experiments. All of this may sound mind-bending, but rest assured, we'll use gentle metaphors and clear images. By the end, you might find that the quantum world, though enigmatic, inspires a serene sense of wonder. So get comfortable, close your eyes if you like, and let's begin our journey into the quiet, twinkling realm of the very small, a journey to discover the quantum realm's secrets as you drift towards sleep. In our everyday experience, we see particles as solid, distinct things, a grain of sand, a drop of rain, and waves as the gentle ripples on water or the sound traveling through air. In the quantum world, however, the line between particles and waves blurs astonishingly. Over a century ago, experiments revealed that light sometimes behaves like a wave and at other times like a particle. For example, in 1801, Thomas Young's famous double-slit experiment showed that a beam of light, when shown through two narrow slits, creates an interference pattern of light and dark bands on a screen, just as ripples on a pond would interfere and form patterns. This was compelling evidence that light is a wave. Yet later, other experiments, like Einstein's explanation of the photoelectric effect in 1905, demonstrated that light also comes in discrete packets called photons, behaving as particles that knock electrons out of metal one by one. Light, it turned out, is both wave and particle, depending on how you look at it. Each photon is an oscillating wave of energy, but also a tiny concentrated spark of energy. Both particle and wave, both spark and rhythm, as a poetic science script once put it. This dual nature isn't unique to light. In 1927, scientists Clinton Davisson and Lester Germer directed a beam of electrons, which we normally think of as material particles, at a crystal and observed an interference pattern, just like waves would produce. Around the same time, George Thomson, the son of J.J. Thomson, who had discovered the electron independently, found the same result with electrons. These experiments proved that matter too can exhibit wave-like behavior. An electron, a grain of matter far smaller than an atom, can spread out like a wave and interfere with itself. In a modern double-slit experiment with electrons, if you fire them one by one at a wall with two slits, a surprising thing happens. Over time, they form a striped interference pattern on a detector screen beyond the slits, as if each electron passed through both slits at once and the two paths interfered. It's as though each electron is a tiny wave washing through both openings, even though we detect it as a single hit, a particle-like point on the screen. How can something be in two places or states at once? To our everyday intuition, it sounds impossible. Obviously impossible from a classical perspective, as one author noted. But in the quantum realm, this is normal. The electron's wave-like nature allows it to explore multiple possibilities simultaneously. Only when we finally detect it on the screen does it choose a definite location to appear. Until that moment, it's as if the electron isn't a localized marble, but a smeared out wave of possibilities. The great physicist Louis de Broglie first proposed this idea in the 1920s, suggesting that every particle has a wave associated with it. And indeed, experiments with not just electrons but atoms and even larger molecules have shown wave-like interference under the right conditions, a striking confirmation of this wave-particle duality at the heart of quantum mechanics. To picture this duality, imagine standing at the shore of a still pond at night. You toss two small stones in, a few feet apart. Ripples spread out from each splash, expanding and overlapping. Where the ripples meet, they create a complex pattern of stronger waves and calm spots, peaks where two waves add up, and troughs where they cancel out. This overlapping of waves is called superposition, a concept we'll explore more soon. Now, picture a single tiny pebble somehow creating that whole pattern on its own, behaving like a wave that goes through both places and interferes with itself. That's essentially what quantum particles like electrons do in the double-slit experiment. When not observed, each particle acts like those overlapping ripples, producing an interference pattern of possibilities. However, the moment we try to observe which slit the particle actually went through, the magic seems to vanish. If we set up a tiny detector at the slits to watch the electrons or photons, the interference pattern disappears. Instead, the particles behave as if each one went through only one slit, yielding just two piles of hits behind the slits with no interference fringes. In other words, when we look, the quantum object chooses a definite path and acts like a particle, not a spread-out wave. The mere act of observing changes the outcome. This is our first encounter with the mysterious observer effect. The quantum world is bashful. In a way, when unobserved, it shows us wavy patterns of probability and interference, but when we peek closely, it collapses. Scientists were astonished by this behavior. As one writer neatly summarized, light and electrons sometimes act like waves and sometimes like particles. Near the slits, they seem to be waves, but when observed, they become particles. Just by observing them, we change the way they act. Even Werner Heisenberg, one of the founders of quantum theory, reflected that at the quantum level, the atoms or elementary particles themselves are not real. They form a world of potentialities or possibilities rather than one of things or facts. In our double slit story, the electron has the potential to go through the left slit or the right slit or both in a superposed wavy way. All possibilities exist simultaneously until an observation forces a single outcome. This is a profound departure from classical common sense, and it truly amazed the early 20th century physicists. Richard Feynman, who loved the double-slit experiment, famously said it contains the only mystery of quantum mechanics, and admitted that nobody really understands quantum mechanics. But don't let that frighten you. Instead, it means you're in good company if you find these ideas a bit mind-boggling. Allow yourself to simply marvel at the strangeness without needing to solve it all. The universe at small scales is playing by different rules, and we can observe and enjoy the pattern like watching a mesmerizing light show, even if we don't see behind the curtain. One of the most enchanting and bewildering quantum principles is called superposition. This is the idea that a quantum system can exist in multiple states at the same time until it is measured or observed. We already met a glimpse of superposition in the double-slit scenario. The electron wasn't just either here or there. It was, in a sense, here and there at once, both slits when we weren't looking. Superposition means a particle can literally take on a combination of possible states simultaneously. It's as if, in the quantum world, nature explores many different stories at once and only settles on one story when we check. Because this concept is so outside everyday experience, physicists often use analogies. One classic analogy is a coin flip. In an ordinary coin toss, once the coin lands, it's either heads or tails. One or the other, a definite outcome. But imagine a coin spinning in mid-air. While it spins, you can't say it's heads or tails. In a sense, it's a blur of both. A spinning coin is not exactly a true quantum superposition. It's really changing rapidly between states, but it gives an intuition of something not pinned down to a single face. A better analogy might be to say, before you look, the quantum coin is as if it were both heads and tails at the same time. Only when it lands and you catch it, i.e. measure it, does it become either one or the other. In formal terms, superposition means the quantum state is a mix, a sum of multiple possible states. But we don't need math to appreciate its magic. We can think in pictures and stories. The most famous story illustrating superposition is Schrödinger's cat. In 1935, the physicist Erwin Schrödinger one of the fathers of quantum mechanics, proposed a thought experiment to highlight how peculiar superposition is when taken to its extreme. He imagined a sealed box containing a cat, along with a very small amount of a radioactive substance, a Geiger counter, and a vial of poison. The setup is such that if one atom of the substance decays, a random quantum event during an hour, the Geiger counter triggers a mechanism to break the vial and release the poison, which would kill the cat. If no atom decays in that hour, the cat lives. The quantum aspect is that the decay of a single atom is governed by quantum uncertainty. After 1 hour, the atom is in a superposition of decayed and not decayed until observed. This means, Schrödinger argued, that the cat would be in a bizarre superposition of alive and dead at the same time until someone opens the box to check. Upon opening, the superposition would collapse, and we'd find either a alive cat or a dead cat, but before that moment, quantum theory suggests the cat state wasn't one or the other. Schrödinger intended this scenario to be absurd, a way to question how or whether the fuzzy quantum rules could apply to everyday big things, a cat as well as tiny particles. He was highlighting a tension in the microscopic realm. Superpositions are routine, but can something as large as a cat really be in a limbo between life and death? Schrödinger himself found it hard to accept. He presented the example to criticize the idea, calling it ridiculous in a sense. Yet, this thought experiment became iconic. It vividly shows superposition's weirdness in a friendly way. Now, in reality, cats, thankfully, don't end up in such quantum limbo in our everyday world, because interactions with the environment and the immense complexity of a large object cause quantum superpositions to decohere and behave classically. But at the level of a few particles, superposition has been repeatedly confirmed in experiments. Particles can be in a superposition of different energy levels, or an electron can be in a superposition of spinning one way and another way, quantum spin states, or a photon can be in a superposition of two different polarizations, orientations of its electromagnetic wave. In fact, even whole atoms and small molecules have been put into superposition states in laboratory conditions. For example, a carbon-60 molecule, a buckyball, has been sent through a double-slit apparatus and exhibited interference, implying it went through both paths at once, a superposition of trajectories. Technology is now harnessing superposition in quantum computers, where a bit qubit can be 0 and 1 at the same time to perform certain calculations in parallel. Nature itself quietly uses superposition. Electrons in atoms exist in clouds of possible positions, not fixed orbits, until interaction makes their position definite. One way to think of it is as overlapping possibilities. Recall the overlapping ripples image, two waves combining into one. If you had a very tiny object that could be in two places, A or B, a quantum superposition would be something like here plus there, a wave that covers both A and B in one combined state. The object isn't fully at A or fully at B. It has probability amplitudes for both. When you measure, you will catch it in either A or B, and the superposition is lost in that moment. We say the wave function collapses to one outcome. But until that interaction, the object exists in a blend of both possibilities. To make it more poetic, imagine you are drifting in a twilight state between waking and dreaming. In a dreamlike way, you see yourself standing in two different beautiful gardens at the same time, one foot in each reality. In one garden, moonlight is falling on white flowers. In another, it's a sunny morning with birds singing. Both scenes overlap in your mind. Only when you fully wake or someone asks, "Where are you?" do you snap into one single reality. That dreamlike overlap is akin to a superposition, a gentle holding of multiple realities, multiple potentials. The quantum world lives in that dreamy overlapping state as a matter of course. It's only when we insist on an answer, when we measure, that nature yields a single outcome. Even though Schrödinger's cat was meant as a paradox, it turns out not to be far from how quantum nature truly behaves at small scales. Superposition is not just a theoretical curiosity, it's an observed fact. If we pass a beam of light through certain crystals or filters, we can create photons in a superposition of polarization states. For example, unpolarized light can be seen as a superposition of vertically and horizontally polarized waves. When you wear polarized sunglasses, you're essentially measuring the polarization of light. Only one component gets through, say, the vertical one, and the other is blocked. Thus, the light is no longer in a mix. It has been forced into one state by that filter. Many such experiments confirm that, before measurement, quantum objects truly behave as if they have multiple tendencies at once, and these tendencies interfere like waves. As soon as measurement happens, one result surfaces and the others vanish. Superposition underlies much of the weirdness of quantum mechanics. It is at the root of entanglement and the observer effect as well. It tells us that definiteness, this or that, is not fundamental. Possibility is fundamental. In a softly philosophical sense, one could say the quantum realm is a realm of potential, where reality exists not as a single track, but as a harmonic chord of many notes, until consciousness or interaction plucks one note from the chord to hear. So as you lie there, consider that all around you, at every moment, countless superpositions are unfolding. The electrons in the atoms of your pillow, the photons of faint starlight coming through your window. All are exploring many states. They settle only when interacting with each other and ultimately with your eyes or instruments. The world at its smallest scales is a tapestry of overlapping maybes. There is something deeply calming in that thought. Reality, at its core, is not solid and unyielding, but flexible, dreamy. Now we venture into what many consider the crown jewel of quantum strangeness, entanglement. If superposition is a mystery of one particle, entanglement is a mystery of two or more particles together. Imagine two particles, say two electrons or two photons, that interact briefly and then separate. Quantum mechanics tells us that sometimes these particles can become entangled, meaning they are not independent of each other even when far apart. They share a kind of unified quantum state. If you make a measurement on one, the other seems to instantly know. and adjust its state accordingly, no matter the distance between them. It's as if you had two coins that were flipped in different locations, and while each coin lands randomly heads or tails, they somehow always mirror each other's results when observed. If one is heads, the other is heads. If one is tails, the other is tails. Even if the two coins are on opposite sides of the world and flipped simultaneously. Such coordination would defy any ordinary explanation, because how could one coin communicate with the other fast enough to correlate their outcomes? This is the essence of entanglement, and it deeply troubled Albert Einstein and others when it was first discussed in the 1930s. Einstein famously derided this idea as spooky action at a distance. In 1935, Einstein, along with Boris Podolsky and Nathan Rosen, published a paper known as the EPR paradox paper, highlighting how, according to quantum theory, measuring one particle could instantaneously affect the state of another distant particle. They considered this an indicator that quantum theory might be incomplete, that perhaps hidden variables, unknown pieces of information, were determining the outcomes in a way we didn't see, so that no real instantaneous spooky influence was needed. Einstein was a realist at heart. He couldn't accept that nature would allow what looked like a violation of the universal speed limit, the speed of light, and of local causality. He asked, in essence, how one particle could know what happened to its partner far away without any signal passing between them. Either information somehow travels faster than light, which Einstein's relativity forbids, or each particle carried some predetermined instruction sheet from the start, hidden variables telling them how to behave when measured. Einstein much preferred the latter idea, that quantum mechanics was incomplete and that a deeper theory would restore a locally realistic picture of the world. Niels Bohr, on the other hand, wasn't disturbed. He responded to EPR by defending the orthodox Copenhagen interpretation that quantum states are not real, standalone properties, but relations between the system and the observer. In Bohr's view, asking which definite state the distant particle has before measurement is meaningless. Bohr believed there was no signal traveling between entangled particles because nothing physically had to travel. The two particles, although separated, formed one quantum system described by one wave function. When you measure one part of that single wave function, the whole wave function collapses, giving correlated outcomes to both parts. From his philosophical standpoint, there was no spookiness, just the non-classical wholeness of quantum systems. Two entangled particles are like two sides of one coin. When you check one side and see heads, you instantly know the other side is tails, yet nothing had to be sent from one side to the other. They were two aspects of the same thing. Bohr extended this kind of reasoning to all of quantum mechanics, what we call reality. In quantum events is only realized at the moment of measurement, and it's fundamentally linked to the whole experimental context, including the measuring devices. Thus, he and Einstein strongly disagreed on this issue. Einstein insisted that each particle must have its own reality, its own definite state or information, even when not observed, an idea we call realism, and that no influence can travel faster than light, an idea called locality. Bohr was comfortable with an anti-realist, or at least non-realist, view. Quantum mechanics doesn't need to describe an objective reality at a distance, only the outcomes of experiments. Their debates, carried out in person at conferences and in print, were intense but always respectful. The Bohr-Einstein debates of the 1920s and 1930s were foundational for the philosophy of physics. Each man was trying to understand what quantum mechanics really implies about nature. For decades after, this spooky action was not just philosophical speculation, it became a subject of experimental tests. John Bell, an Irish physicist, entered the scene in 1964 with a remarkable breakthrough. He derived a theorem, Bell's theorem, that showed a way to test whether Einstein's idea of local hidden variables could explain quantum correlations, or whether the quantum predictions with entanglement intact prevailed. Bell formulated an inequality, now known as Bell's inequality, that any local realistic theory must obey. Quantum mechanics, in certain situations with entangled particles, predicted that this inequality would be violated. In essence, Bell provided a concrete mathematical way to distinguish Einstein's universe from Bohr's universe. It took some time, but by the 1970s and 1980s, technology allowed physicists to perform Bell test experiments. Pioneers like Alain Aspect in 1982 conducted experiments with entangled photons, measuring their polarizations in different directions. The results were striking. The correlations between distant photons violated Bell's inequality, in agreement with quantum mechanics and contrary to any theory of local hidden variables. In plain language, the experiments showed that the entangled particles were indeed behaving in that spooky connected way that quantum theory predicted. And no explanation with pre-existing local properties could account for the outcomes. Over the years, these experiments have been repeated and refined with longer distances, fast switching measurement settings, closing various loopholes. By 2015, multiple independent experiments in Delft, Vienna, etc., closed the last major loopholes, giving very high confidence that entanglement is real and no ordinary signal or classical mechanism is behind it. For these groundbreaking studies, Alain Aspect, along with John Clauser and Anton Zeilinger, were awarded the 2022 Nobel Prize in Physics. The verdict of nature seems clear. Einstein's instinct that no spooky action should exist was wrong, or if not wrong, at least nature doesn't follow the constraints of locality and realism that he hoped for. Entanglement is a genuine feature of the world. So what is entanglement like? Let's paint a mental picture. Picture 2 twinned photons born from a single source. For instance, when an atom emits 2 photons that fly off in opposite directions, these photons might be entangled in polarization. Each one's orientation is undefined until measured, but they will always agree or always be opposite, depending on how they were prepared. Now imagine one photon travels to a detector near you, and the other photon travels to a detector on the far side of the moon. If they are entangled, then even with that great distance, there is a single shared quantum state describing both. If you gently measure the polarization of the photon near you and find, say, it is polarized vertical, then instantly in that very same moment, the photon on the moon will have a polarization state determined in relation to yours. If they were set to always match, it will now be vertical as well. If they were set opposite, it will be horizontal, etc. Before you measured, neither photon had a definite polarization. They were in a superposition of possibilities, correlated but not fixed. Your measurement forced the pair as a whole to pick an outcome, and thus the distant photon had to pick a complementary outcome. It's as if these two photons are two sides of one coin, or two dancers in a perfectly synchronized routine, mirroring each other's moves instantaneously. Importantly, and this is often emphasized, entanglement cannot be used to send meaningful messages faster than light. While the effect is instantaneous, it's more like the universe flipping two coins that always land the same way. You see your result, and instantly you know what the other must be, but you couldn't choose your result in advance. Eight. So you can't encode a message in the outcomes, because you can't control them. You can only later compare notes with your partner who measured the other particle and confirm, wow, we always got opposite results, or always the same, etc. That comparison still requires normal communication at light speed or slower. So Einstein's relativity survives in the sense that no useful information travels faster than light. But something deeply fundamental, correlation, oneness, call it what you will. Entangled particles behave as if distance doesn't truly separate them. In the quantum realm, space and time can seem to bend or even evaporate, and connection can trump separation. This spooky connection has been confirmed. Even over vast distances, experiments have entangled particles separated by many kilometers. And every test continues to support the quantum description. The world, bizarrely, is entangled at its core. We believe that many particles can be entangled in complex ways. Think of it like many musical instruments, all part of one symphony. You can't describe one instrument's music without the context of the whole orchestra. Some theorists even suggest that entanglement might underlie the very fabric of space-time itself. A speculative but fascinating idea that perhaps space-time geometry emerges from quantum entanglement, as seen in some recent work connecting quantum information and gravity. For our purposes tonight, we can simply savor the strangeness. Once connected, always connected. As NASA described it, particles of common origin remain linked, sharing a united state forever. If you could see entangled particles, you might imagine a faint ethereal thread or beam of light between them, pulling them into a single dance. No matter how far they drift, if one dancer sways left, the other, in perfect tandem, sways right in the same moment. It defies our normal sense of separation. The universe, through entanglement, whispers to us that distance is not absolute. At a fundamental level, everything can be seen as part of one connected whole. As you lie there, consider that somewhere out there, two photons born in a distant star's heart millions of years ago might be entangled, flying through the cosmos. When one strikes a piece of interstellar dust and is absorbed, the other instantly feels that loss of its twin and takes on a definite state in response. The universe is full of these silent quantum threads. The very light in your room from a lamp or from your phone screen consists of countless photon pairs created in processes that could be entangled. And while we don't notice any odd effects in daily life, because entanglement is fragile and easily broken by interactions, it's continuously at play in the subatomic domain. Einstein might have been uncomfortable with it, but even he had to admit nature might be subtle in ways we hadn't expected. In one letter, frustrated, he referred to the Heisenberg-Bohr tranquilizing philosophy as a kind of soothing pillow that stops people from worrying about the deeper reality. He was implying that Bohr's attitude, "Don't ask what's really happening, just calculate the probabilities," was too content with mystery. Ironically, tonight we are using these quantum mysteries as a tranquilizing pillow, but in a positive way, we're letting the profound strangeness and unity of the quantum world lull us into a state of awe and calm. There's something almost spiritual about entanglement. It suggests a universe where, at some deep level, everything is connected to everything else. As one writer put it, if classical physics is like our normal, solid reality, quantum physics is like an alternate universe where an apple can be on a table and on Mars at the same time, and even be tied to another apple light years away through entanglement. It's a universe of endless possibilities and intimate connections. By now, a subtle theme has been weaving through our exploration: the role of the observer. We've seen that when we observe or measure, superpositions collapse into definite states, and wave-like particles become particle-like. This is often referred to as the observer effect in quantum mechanics, the notion that the act of measurement affects the system being measured. But let's clarify, it's not consciousness or human mind per se that causes the effect. At least, standard quantum theory doesn't require a human observer, a detector, or any interaction will do. It's the physical interaction necessary to observe something that disturbs the quantum system and changes the outcome. In our double-slit story, for instance, to observe which slit an electron goes through, one must have some device at the slit. Perhaps a tiny laser or some sensor that the electron would interact with. That interaction inevitably adds a disturbance. It's a bit like trying to watch a shy firefly in a dark room. If you shine a flashlight on it to see it, the light itself might startle the firefly and change its behavior. On the quantum scale, any measurement is like shining a light or otherwise interacting with the particle, and thus you cannot measure a quantum system without altering it in some way. Werner Heisenberg quantified one aspect of this with his famous uncertainty principle in 1927. It says that certain pairs of properties, like a particle's position and momentum, cannot both be known to arbitrary precision at the same time. The more precisely you measure the position, the more you disturb the particle, and the less certain its momentum becomes, and vice versa. This isn't just a matter of instrument accuracy, it's a fundamental limit, a trade-off built into nature. One way to think of it, if you want to see exactly where an electron is, you might hit it with a high-energy photon, light, to get a sharp image, but that photon will kick the electron, changing its momentum unpredictably. If you try to gently measure momentum, you must use long-wavelength, low-energy light that doesn't disturb momentum much, but that light is too fuzzy to resolve position well. So, there's an intrinsic blur to knowledge at quantum scales. The act of observing one aspect blurs another. Philosophically, this raises a profound question. Do quantum particles have properties like position, momentum, etc., when we're not observing them? Einstein would say yes. The moon is still there when no one looks, and likewise an electron has some real position even if we don't know it. Bohr would say the question is meaningless. The electron doesn't have a definite position in between observations. It only has potentialities described by a wave function. In the Bohr view, asking what is really happening when not observed is like asking what is the sound of a tree falling in a forest with no one to hear. If truly no interaction occurs, quantum theory gives us no answer, only probabilities for when an interaction does happen. The observer effect in quantum mechanics is sometimes misstated as consciousness creates reality. That's an overstatement. Mainstream physics doesn't require a conscious mind, just an interaction or measurement apparatus. However, it does force us to acknowledge that the act of measurement plays a key role in what outcomes we see. In classical physics, we think of measuring as just revealing a pre-existing property, like reading a thermometer tells us the temperature that's already there. In quantum physics, measuring participates in producing the outcome. It's almost as if the universe at small scales is like a delicate music that can play in many keys, and an observation is like choosing an instrument that causes the music to resolve in a particular key. One interesting extension of the observer effect is the notion of the quantum observer not necessarily being human. For example, in an experiment, a camera can record which slit a particle went through, but if nobody looks at the footage, did that constitute an observation? Quantum mechanically, if the information about the path gets recorded in any way, even in a device or in the environment, the interference is destroyed. In a rather mind-bending variant, scientists have set up experiments where they record which path information with a device, but then sometimes erase that information before anyone sees it. And they find that if the information is truly erased, like the universe itself never knew the path in an irreversible way, the interference pattern can be restored. These are called quantum eraser experiments. This implies that it's not human consciousness specifically, but the irreversible imprint of information that constitutes an observation in quantum terms. The universe behaves one way if information could in principle reveal an outcome, and another way if no such information is left accessible. The observer effect also merges into the concept of wave function collapse. Schrödinger's wave function, the mathematical object that describes a superposition, is said to collapse upon measurement, randomly picking one of the possible states. This collapse is instantaneous in the mathematics, and it's how the theory yields definite results when we observe. But the mechanism of collapse, or even whether collapse is a fundamental physical process or just an apparent change in our knowledge, is still debated. Some interpretations of quantum mechanics, like the many worlds interpretation, even do away with collapse entirely, suggesting that all outcomes happen in branching universes and we only ever see one branch. Others propose that some interaction with the environment decoherence effectively achieves the same result as collapse without needing a special observer role. Without delving into those deep waters, we can appreciate the simple truth the observer effect teaches us. The quantum world does not separate the observed from the observer in the way classical thought did. As one quantum physicist, Pascual Jordan, said, "Observations not only disturb what is to be measured, they produce it. The measurement is part of the reality-making process." The universe at the quantum level is participatory. It's as if the questions we ask through experiments shape the answers we get. In a dreamy sense, one could say reality is half built by the world, half built by how we look at it. This idea resonates with some philosophies and even with certain spiritual perspectives, but here it arises from hard experimental fact. Measuring changes what is measured. Wheeler, a famous physicist, even mused about a participatory universe. He imagined a scenario called the delayed choice experiment, a form of which has been done where decisions made after a photon passes through a double slit can seemingly retroactively determine whether it behaved like a wave or particle. The conclusion was that quantum phenomena don't decide in advance. Only when measured do they take on reality for that measurement. It's as though reality remains fluid and ambiguous until the very end when a question is asked. This might sound unsettling, but we can also find it profound and beautiful. It means that, at some fundamental level, we are not mere bystanders to the universe. Even as passive observers, our interaction just by shining a light to see, or by having particles bump into our detectors, becomes part of the story. We are woven into the cosmic tapestry that we observe. In a gentle bedtime thought, the act of observing a star in the night sky with your eyes completes a story that might have begun hundreds of years ago when the star's light started traveling toward Earth. The photons from that star were in a sense in limbo, traveling as expanding probability waves across light years. When they enter your eye and hit the retinal cells, they are observed. Their wave function collapses and they cause a chemical reaction that leads to your perception of starlight. The observer, you, and the observed, starlight photon, meet and create an event of seeing. Until that happened, one could say the photon's existence was smeared out in possibility. It might have just missed Earth or hit a different atom in the atmosphere, etc. The universe offered many possible paths, and the act of observation realized one. In our relaxed exploration, we don't need to worry about the technical details. Instead, we can take a poetic view. Reality blooms where consciousness, or at least interaction, touches it. It's like a vast dark field where flowers of reality open up wherever a beam of attention or interaction shines. Some even liken it to the idea that the universe wants to be observed, or that meaning requires participation. The observer effect reminds us that the classical idea of an objective world separate from us isn't the whole story. The quantum realm suggests unity between the knower and the known. As you gently breathe and sink deeper into relaxation, think of yourself not as isolated from the world around you, but intimately connected. The very atoms in your body are constantly observing and interacting with each other. In fact, if quantum phenomena didn't collapse or settle due to constant interactions with air molecules, ambient photons, etc., the macroscopic world would be very fuzzy indeed. Thankfully, in daily life, interactions abound, so things appear solid and well-defined. But on the edges of what is known, when things are very isolated and small, the universe behaves more like a poem than a piece of clockwork. It allows myriad possibilities, and the story unfolds only as it is read. We've touched on the philosophical debate between Einstein and Bohr, which really boils down to a question: what is the quantum world telling us about reality? The phenomena of superposition, entanglement, and observer-dependent outcomes challenge our intuitions. Two main philosophical camps emerged historically. Realism, Einstein's camp. This is the idea that physical properties have definite values independent of observation. In other words, quantum particles do have a real state, possibly hidden even when we're not measuring them. Einstein believed there should be an objective reality out there, and that quantum mechanics, as weird as it is, must be an incomplete description, a stopgap until a deeper theory with hidden variables or some new principles explains things in classical-like terms. He was uncomfortable with probabilities and with the idea that the act of measurement creates the result. He famously said, "I like to think the moon is there even if I am not looking at it," highlighting his belief that observation isn't what makes the moon real. He also quipped about quantum randomness. God does not play dice with the universe, expressing his suspicion of indeterminism. Copenhagen. Interpretation, Bohr's camp. Bohr and his colleagues, like Werner Heisenberg, took a more anti-realist or agnostic stance about reality. They argued that quantum mechanics doesn't describe an objective reality, it describes our knowledge or experience of phenomena. According to Bohr, asking what a particle really is, beyond the experimental context, is asking for an ill-defined thing. The Copenhagen view emphasizes that quantum mechanics gives us the tools to predict results of experiments, and that's it. Don't ask what the electron really is doing in between. That's not a question. This view accepts indeterminism fully. Outcomes are fundamentally probabilistic, not determined by hidden facts. Bohr thought that trying to assign definite classical attributes to a quantum system when those attributes aren't measured is a mistake. One must respect the principle of complementarity, that objects have complementary aspects. In essence, reality for Bohr was a kind of play of phenomena and the term reality. Beyond that was either meaningless or at least not useful in physics. This is often called an anti-realist stance, though some debate if Bohr was truly anti-realist or just redefining what we mean by reality. During the Solvay Conference of 1927, Einstein peppered Bohr with thought experiments trying to expose some inconsistency or incompleteness in quantum mechanics. Every time, Bohr somehow parried Einstein's challenge with a quantum explanation that upheld uncertainty and complementarity, much to Einstein's frustration. By the 1930s, the orthodox Copenhagen interpretation reigned in physics. Education, students were told essentially, "This is how it is, don't worry about the why." Physicist David Merman summarized the Copenhagen attitude as "shut up and calculate," meaning the theory works, so use it to get numbers and don't ask metaphysical questions. Many did just that, pushing forward with applications and new fields, leaving the interpretation puzzle aside. But the questions never fully went away. Einstein died in 1955, still convinced quantum mechanics was not the final word. Bohr died in 1962, confident that quantum mechanics, while counterintuitive, was complete in its domain. The Bell experiments later, 1960s, 1980s, provided a kind of answer. They showed that any theory which has Einstein's kind of strict realism plus locality cannot reproduce the actual results we see. So in a way, they vindicated Bohr, or at least standard quantum mechanics, on the specific issue of entanglement. However, interpreting what that means is another matter. It doesn't automatically tell us how to picture reality, only that the quantum description holds up. Today, there are multiple interpretations of quantum mechanics. Some, like many worlds, Everett's interpretation suggests that whenever a quantum event seems random, in fact the universe splits. In one branch, the cat is alive, in another, it's dead, and we simply find ourselves in one branch. This removes the randomness and observer-caused collapse at the cost of believing in a constantly branching multiverse where all outcomes happen. It's a very realist picture. Quantum state, always evolving, nothing special about measurement aside from our subjective experience splitting. Another interpretation, Bohmian mechanics, pilot wave theory, introduces hidden variables and a guiding wave. Particles always have definite positions, so realism is saved, but they're guided by a non-local pilot wave that ensures they still do the weird quantum things. So entanglement and non-local effects are explained by an invisible hand, so to speak. This theory reproduces all quantum predictions, but at the cost of making instantaneous connections a fundamental feature. Non-locality is built in. There's also cubism, quantum Bayesianism, which says the wave function is just the observer's personal information about the system, a radical subjectivist view of quantum states. And others, like the objective collapse theories, which modify quantum mechanics slightly to have wave functions collapse on their own after a certain size or time, thereby bridging quantum and classical. These are speculative and being tested. The remarkable thing is, despite these varied interpretations, the raw quantum theory and its experimental support remain unchanged. You can choose an interpretation that feels most comfortable, but no experiment yet has told us definitively which interpretation, if any, is correct. It's as if quantum mechanics is a Möbius strip. You can twist and turn your understanding, but you end up in the same place with the same phenomena. Einstein lost the specific battles. Quantum theory works too well to be wrong, and Bell tests ruled out his preferred type of hidden variables, but the war for understanding reality is still ongoing. Perhaps Bohr's view triumphed in practice, yet even Bohr's interpretation is not fully satisfying for some. It leaves a feeling of, yes, but what is really happening? Generations of physicists have learned to live with a kind of pragmatic silence on that question. They calculate and build technologies like lasers, transistors, MRI machines, all relying on quantum physics, and the philosophical oddities are often set aside. But when we pause, like we're doing now, in a quiet and reflective moment, it's hard not to wonder, what does it all mean? Is the quantum world telling us that reality is fundamentally mental or informational, since observation is key? Or that there are countless parallel realities, many worlds? Or that the ordinary notion of space-time is secondary to a deeper network of entanglements? These are deep questions that can swirl in your mind without needing immediate answers. In the gentle spirit of our session, think of it this way. The quantum realm's secrets invite us to be comfortable with paradox. We can hold two seemingly opposed ideas, like Einstein's realism and Bohr's empiricism, in our minds, just as a quantum particle holds multiple states. We can find a peaceful balance in not fully knowing, but deeply appreciating the mystery. In a way, this mirrors certain philosophical or even mystical traditions that emphasize embracing the unknown. One interpretation might resonate more with you. If you like the idea of a connected cosmos, you might lean toward seeing entanglement as a sign of underlying unity, something almost spiritual, where separation is an illusion. If you like the idea of concrete reality, you might imagine there are hidden variables or many worlds where things are determined just out of sight. The wonderful thing is, as far as day-to-day life and even practical science is concerned, you can adopt any of these views and still predict things correctly with the quantum math. It's a reminder that humans seek meaning and narrative, but nature just is. The quantum world doesn't come with an easy storyline. We impose one to satisfy our understanding. Niels Bohr had a quote: "If quantum mechanics hasn't profoundly shocked you, you haven't understood it yet." By that measure, feeling a bit perplexed is a sign you do get how revolutionary these ideas are. But let that shock give way to admiration. We are discovering that reality is far more subtle and rich than our senses tell us. At small scales, particles flicker in and out of ghostly superpositions. Distant events can be eerily correlated, and what we call a fact might depend on how it's observed. The quantum realm humbles us, yet it also enchants us with its depth. As one scientist put it, the world is not only stranger than we think, it's stranger than we can think. And yet, we've managed to uncover these secrets through experiments and equations, shining a light, quite literally, on nature's smallest scales. We've journeyed through superposition, wave-particle duality, entanglement, and the role of the observer, each a jewel of mystery in the quantum crown. At this point, you may feel that the ground of reality is a bit less solid than when we started. But rather than finding that alarming, you might find it liberating or soothing. The rigidity of classical expectations has softened into a quantum twilight, where things can be two things at once, where certainty gives way to probability, and where connections exist beyond visible touch. There is a profound calm in accepting that not everything needs to be sharply defined. The quantum realm's secrets encourage us to live with questions, to make peace with ambiguity, and to revel in the marvel that existence is not trivial. As the writer Larry Gottlieb concluded in his musings on quantum observers, the world itself will always be unknowable, unfathomable, and mysterious to us. That's not a problem. It's the source of the possibility of magical experience. In other words, the very unknowability is what makes the universe a continuous source of wonder. Think of how the stars in the night sky are beautiful, partly because they are distant and enigmatic. In the same way, the quantum world is beautiful because it defies our complete understanding, inviting endless exploration. We started by imagining a descent into the microscopic. Let's end by imagining the wisdom we bring back from that journey. we have seen that reality has layers: the surface layer of everyday objects and a deeper layer of quantum probability and entanglement. Both are true in their own domains. We live in the everyday layer, but knowing about the deeper layer can give us a new perspective on life. For instance, consider how interconnected things are. Entanglement literally connects particles across space. Even if most entanglement is washed out at macroscopic scales, it tells us that our universe has fundamental threads linking events. In a poetic sense, one can see this as a hint that separateness is an illusion. Everything originated in the Big Bang as one blob of quantum stuff, and some of that original entanglement might still persist here and there. We are all made of stardust, and perhaps in some manner of speaking, the atoms in your body carry ancient entanglements with atoms across the cosmos. We don't have evidence of human-scale quantum effects in daily life. No, you can't entangle brains or anything so grand, not with current technology at least. But simply knowing that nature permits such intimacy at a distance can inspire a feeling of connectedness. Or consider possibility. Quantum superposition means the future isn't strictly determined. There are genuine possibilities and chance at play. This allowed one eminent physicist, Freeman Dyson, to remark that quantum mechanics is what makes life possible. Because if everything were predetermined and rigid, life's flexibility and evolution might not work. The indeterminacy at small scales allows for novelty and creativity in the unfolding of the universe. There is randomness, yes, but randomness can be seen as nature's freedom. At the smallest scales, there is a little wiggle room that can amplify into larger differences, like a mutation in DNA coming from a quantum event. Perhaps this is how the universe writes itself into being, with a dash of spontaneity. For us, it's a reminder to cherish possibilities. Even when things seem certain, at a deeper level, there's a playfulness in how outcomes come to be. And what about the role of the observer? It teaches us humility and responsibility. It says we can't always stand apart from what we study or affect. Simply by existing and interacting, we change the world. Every measurement, every touch, every choice has ripples. Of course, in quantum terms, those ripples are subtle and subatomic, but philosophically, it aligns with the sense that we are participants in reality, not just spectators. It's like a grand play where we thought we were the audience, but in fact, we are actors too, inseparable from the scene. As you drift off to sleep, let these ideas float lightly in your mind, not as hard puzzles to solve, but as wonders to appreciate. See if you can visualize the quantum world in a dreamlike way, a field of shimmering possibilities where electrons dance as waves and particles, where two photons apart by galaxies share a secret handshake, where a cat in a box can be alive and purring and silent and still at once, where the simple act of looking can create reality. It's a place both surreal and serene. Surreal in concept, but serene in that it follows its own elegant logic. Quantum physics is often described with words like strange, weird, puzzling, but it's also deeply harmonious. The equations of quantum mechanics, which we spared you tonight, are full of symmetries and beauty. The phenomena, as odd as they sound, follow mathematical patterns that are stunningly accurate. So, there is order in the mystery, a kind of higher order that we are still grasping to fully interpret. In a sense, the quantum realm is a reminder that the universe is far more creative and clever than our everyday senses reveal. It encourages a mindset of openness. When you wake, the classical world of breakfast tables and blue skies will feel stable and normal as ever. But maybe, just maybe, a part of you will carry a subtle appreciation that underneath that solidity is a miracle of light and probability. Every solid object is sustained by quantum forces and exchanges virtual particles with empty space. Every ray of light is both an electromagnetic wave and a stream of photons born from quantum jumps in atoms. We live supported at all times by quantum phenomena in the microscopic engine room of reality. Remember, the world is definitely a weirder place than we'd like to believe. In that weirdness lies creativity, potential, and perhaps the secrets to existence itself. As you close your eyes and your brain waves slow, imagine them sinking with the gentle waves of possibility at the quantum level. You are, in a way, made of quantum particles too. Every atom in you follows these rules. But through an emergent miracle, they've combined to create a warm, conscious being who can contemplate the universe. How wonderful is that? From quarks to thoughts, it's all one continuous story of complexity arising from simple, subtle rules. In the silence of your room, with the outside world dimmed, you might feel a kinship with the quiet quantum world. Both are calm, soft, and full of latent energy. There's a famous Zen-like saying by physicist John Wheeler: "We are participators in bringing about something of the universe in the distant past, and if I might paraphrase it, in a way the universe has a way of looking at itself through us." So as you sleep, the universe, through your very existence, is contemplating itself. Our exploration of the quantum realm has been one way of that self-reflection. Now, let any remaining analytical thoughts subside. You can always revisit these ideas when you're awake and curious. For now, let the feeling of wonder remain without the need for analysis. Feel the gentle assurance that it's all right not to have all the answers. Even the greatest minds didn't. Einstein, Bohr, Schrödinger, they all wrestled with these questions and found no final resolution, yet they expressed profound admiration for nature's mystery. Einstein said, "The most beautiful thing we can experience is the mysterious." That fits perfectly here. That fits perfectly here. You've experienced the mysterious tonight. As you drift into sleep, breathing slowly, imagine that you too are a wave on a vast ocean of possibilities. In sleep, our minds let go of fixed reality and wander through dream superpositions, in a way, a very quantum thing to do. Embrace that state. You are safe. You are part of a grand, mysterious cosmos, and there is beauty at every scale of existence. From the quantum phone to the galaxies, from the electrons to your own heart, everything is interconnected and evolving in harmony beyond full understanding. And that is perfectly fine. Tomorrow's sun will rise as a blazing fusion reactor powered by quantum tunneling in the star's core, and you will go about your day in the familiar classical world. But perhaps with a new sparkle in your eye, knowing the air and light around you hold quantum secrets in every particle. You carry a bit of that secret now in your relaxed, sleeping mind. Sleep well and let the quantum realm secrets guard your dreams, reminding you that reality is deeper, stranger, and more wonderful than it seems.